In this video, we will be continuing our discussion of the chapter of polynomials, and we will be covering the topic of factorization of polynomials. So first, let us try to understand what do we mean by factorization. If we are given a polynomial with some degree n, we want to represent that polynomial as a product of smaller degree polynomials. So if the polynomial has a degree n, we want to represent that polynomial as some other polynomials, as the product of some other polynomials whose degrees are less than n. So that when we multiply those smaller degree polynomials, we get back our original polynomial of that higher degree. So how to do that factorization, we will cover that later, but for the most part of this video, we are going to only see how to check whether a certain binomial is a factor or not of a certain polynomial. So again, binomial is a polynomial which has only two terms. So we have one term of x and another term of the constant term. So a binomial is a polynomial containing only two terms. And this part of the video, or this particular video, is going to focus on how to check whether a certain binomial is a factor of the given polynomial or not. Okay, in the next video we will actually see how to factorize the polynomial and obtain lower degree polynomials which are factors of the higher degree polynomial. Okay, we'll do that in the next video. Now, to check whether a given binomial is a factor of a polynomial or not, we are going to use two different theorems. One of two different theorems. The first one is the remainder theorem. So we'll see what the remainder theorem is, and the second theorem that we will see is called as the factor theorem. By using one of these theorems, we will be able to check whether a given binomial is a factor of a polynomial or not. Now, what does the remainder theorem say? If we have a polynomial p of x that is divided by a binomial, say x minus a, where a is any number, any real number, then the remainder theorem states that the remainder is given by the expression p of a. That means whatever is this a here in this x minus a, we have to substitute that a in the polynomial expression p of x, and we get p of a, and that p of a gives us the remainder of that division. So when a polynomial p of x is divided by a binomial, the remainder of that division is given by evaluating the polynomial p of x at the value a. So based on this, we can write the polynomial p of x as the divisor x minus a times the quotient plus the remainder. Now, just to illustrate this, I'll give you an example with the simple numbers. So when we divide two numbers, so let's say I'm dividing the number 7 by the number 2. Okay, so when we divide 7 by 2, 2 goes into 7 3 times, so we get 2 3s are 6, and when we subtract this, we get a remainder of 1. So now what is the answer that we have got? This is nothing but the quotient, which we will denote as q. What we have here is the remainder, we'll call that as r, and clearly you can see that the number 7 can be represented as 2 times the quotient, that is 2 times 3, plus the remainder, which is 1. So this is basically 2 times the quotient plus the remainder, and that is exactly what is being represented here. If we have p of x, a polynomial p of x divided by x minus a, then that p of x can be represented as x minus a times the quotient plus the remainder. So when we are dividing 7 by 2, 7 is 2 times the quotient plus the remainder. So if we had p of x divided by x minus a, then p of x can be written as x minus a times the quotient plus the remainder. Okay, and this is what the remainder theorem tells us, that the remainder is given by evaluating the polynomial at x equals a. Okay, that is p of a. So q of x is the quotient, which will be some polynomial in x. Okay, so this is what the remainder theorem states, and what will happen if the value of P of A turns out to be 0, and that is what the factor theorem leads us to. So now going forward from the remainder theorem, if we divide a polynomial P of x with some binomial x minus a, then we can say that x minus a is a factor of P of x if P of a equals 0. So that means if we take that number a and substitute in the polynomial x, and if that evaluates to 0, then that x minus a is a factor of P of x. So basically here, if x minus a is a factor of Q of x, then there will be no remainder, right? The remainder should be 0. For example, instead of 7, let's say we divided 6 by 2, so we get 2 3s are 6, and the remainder is 0. So in that case, the 6 is 2 times 3 plus the 0 remainder. So that means 2 is a factor of 6. 2 goes exactly in 6. So therefore there is no remainder here. So similarly here for the polynomials, if we have a divisor which is a factor of the given polynomial, then there will be no remainder. That is, the remainder will be 0. That means P of A will be 0. So if the remainder is 0, then that divisor is a factor of the polynomial P of x, and that is what the factor theorem is telling us. So x minus a is a factor of P of x if P of a, that is the remainder, is equal to 0. Or conversely, we can state that as if the remainder is 0, that is if P of a equals 0, because P of a is basically the remainder. So if the remainder is 0 when dividing P of x by x minus a, then we can say that, or we can conclude that x minus a is a factor of P of x. So these two statements are basically converses of each other. So we can say that x minus a is a factor of P of x if the remainder is 0, or conversely, if the remainder is 0, then we can conclude that x minus a is a factor of P of x. Okay, so we'll just look back at the expression from the remainder theorem, where we have the polynomial P of x represented as the divisor times the quotient plus the remainder. So Q of x is some polynomial which gives us the quotient of that division, so plus the remainder. So if the x minus a, the divisor, is a factor of P of x, then the remainder is 0. So therefore, if P of a is 0, then this term will disappear. So we will have P of x as simply x minus a times the quotient. So just as we had for dividing the number 6 by 2, so it's 2 times 3 6 plus the remainder is 0. So you'll simply write it as 2 times the quotient. So similarly here, the divisor times the quotient, because the remainder is 0. So clearly we are able to represent P of x as a product of two polynomials, and that means x minus a is a factor of P of x. Or conversely, we can say that if x minus a is a factor of P of x, then this P of x with the remainder of 0 should evaluate to 0 at a. So when we substitute x equal to a in the polynomial, we get 0. So when we put in place of x, if we substitute a, so we get a minus a times q of a, and a minus a is 0, and 0 times anything is 0. So therefore we clearly see that x minus a is indeed a factor. Okay, or in other words, if x minus a is a factor of the polynomial, then the remainder is 0. So P of a is 0. Okay, so the whole idea is that if we are given a divisor or a binomial, and we are asked to check whether that particular binomial is a factor of a polynomial or not, all we have to do is we first obtain the 0 of that binomial. That means we'll equate x minus a to 0, and we'll get x equal to a. And that value of a, that value of x, we will substitute in the polynomial and check if we get the remainder as 0. If the remainder is 0, we will say that x minus a is a factor. If the remainder is not equal to 0, then we will say that x minus a is not a factor of the polynomial P of x. So let us do some examples. So we are given a polynomial here, P of x, and and another polynomial s of x, and we are asked to find whether, or we are asked to check whether this binomial x plus 2 is a factor of these two polynomials or not. So the first thing we will do is we will find the 0 of x plus 2. So let me write that. 0 of x plus 2 is obtained by equating x plus 2 to 0. Okay, so that means when we put x plus 2 equals 0, that means we get x equals minus 2. Okay, so once we get the 0 of x plus 2, we will use that value of x in the polynomial expressions and see if that evaluates to 0 at x equal to minus 2. If it evaluates to 0, then x equals to minus 2 is a root or 0 of the given polynomial, or in other words, x plus 2 will be a factor of this particular polynomial. So let's do for p of x. So we want to find p of minus 2. So p of minus 2 is, we will put wherever there is x, we'll substitute minus 2. So it's minus 2 cube plus 3 times minus 2 square plus 5 times minus 2 plus 6. So that will be minus 2 cube is minus 8. Minus 2 square is plus 4. Plus 4 into 3 is plus 12. 5 into minus 2 is minus 10 and plus 6. So what does that evaluate to? So we have here 12 minus 8 is 4, and minus 10 plus 6 is minus 4. So we have effectively this is equal to 0. So we have minus 8 minus 10 is minus 18, and 12 plus 6 is plus 18. So minus 18 plus 18 is 0. So clearly we can see that when we substitute x equals minus 2 in the polynomial p of x, we get an answer of 0. So that means the remainder is 0. So that means when we divide p of x by x plus 2, the remainder is 0. So the remainder is p of a. So in general it is x minus a. So when you have x minus a, it is x minus, in this case it is plus, so it's x minus minus 2. So that's why we get x equal to minus 2 here. So the value of a is minus 2. So when you substitute minus 2 in the polynomial, we get 0. That means the remainder is 0. If the remainder is 0, that means x plus 2 divides the polynomial perfectly without any remainder. That means x plus 2 is a factor of p of x. So therefore, we can say that x plus 2 is a factor of p of x. So similarly, we can check whether x plus 2 is a factor of s of x. So we are given s of x is 2x plus 4. So we want to find s of minus 2. So in place of x, we just substitute minus 2. So we'll get 2 into minus 2 plus 4, which is minus 4 plus 4, which is equal to 0. So that means s of a is 0. That means the remainder is 0. So therefore x plus 2 is a factor of s of x. Okay, so we have checked whether x plus 2 is a factor of each of these. So basically what we do is we take the 0 of x plus 2 and substitute that in the polynomial expressions and see if that polynomial evaluates to 0 for that value of the 0 of x plus 2. And if it is equal to 0, then we say x plus 2 is a factor. If it is not equal to 0, it will be, or you can conclude that x plus 2 is not a factor. So in this particular case, x plus 2 is a factor of both these polynomials. And in fact, for the second case, we can clearly see that we can write this s of x, we write the x properly, s of x, which is 2x plus 4. If we take the 2 as a common factor, so we'll get 2 into x plus 2. So basically we can see that 2x plus 4 is 2 into x plus 2. That means for 2x plus 4, one of the factor is 2 and the other factor is x plus 2. So we are able to represent 2x plus 4 as a product of two terms, 2 and x plus 2. So each of these two terms are factors of the polynomial. So x plus 2 is clearly a factor of 2x plus 4, okay, and which is what we have verified here as well. When we substitute x equal to minus 2 in the polynomial, it evaluates to 0. That means basically this is the remainder after that division by x plus 2, so the remainder is 0, okay. Let's move on to the next problem, next example. Here again we are given that x minus 1 is a factor of this polynomial, and given that x minus 1 is a factor, we are asked to evaluate this constant term k, okay. The value of k is not given to us, so we are asked to find the value of k, and the information we have is that x minus 1 is a factor of this polynomial. So the 0 of x minus 1 is x equal to 1. 0 of x minus 1 is obtained as x minus 1 equals 0. So that means x equals 1. So x equal to 1 is the 0 of the binomial x minus 1. So if x minus 1 is a factor of this p of x, if x minus 1 is a factor of p of x, then p of 1 should be equal to 0. That is what the factor theorem states. So if we have a binomial as a factor of a polynomial, then the remainder must be 0. So we basically have to evaluate this polynomial at x equal to 1 and equate it to 0. So that means 4. So let me write that p of 1 equals 4 into 1 cube plus 3 into 1 square minus 4 into 1 plus k equals 0. So we equate that to 0 because we are given that x minus 1 is a factor. Therefore, p of 1 must be equal to 0. So we just equate that and solve for k. So that will give us 4 plus 3 minus 4 plus k equals 0. So 4 minus 4 will go off. So we'll have only k plus 3 equals 0. So that implies that k equals minus 3, okay. So we take the 3 to the other side and we get k equal to minus 3 as our answer for the value of k. So fairly straightforward, okay. In this case we are given that x minus 1 is a factor, and therefore we equated the remainder to 0 to obtain the value of k, okay. So if the remainder is 0, then x minus 1 is a factor. If x minus 1 is a factor, then the remainder must be 0. So these are two converse statements of each other, and using that we are able to find the value of k in this particular case. Okay, now let's move on to some exercise problems, and we will solve these problems. Again, basically we are not going to factorize the polynomials, okay. We'll leave that for until the next video. In this particular video, our focus will only be on checking whether a given binomial is a factor or not of the given polynomials, and for that we will be using the factor theorem. So basically we will take the 0 of the divisor, which is the binomial, and substitute it in each of the polynomials and see if it evaluates to 0. So basically we are checking whether the remainder is 0 or not. If the remainder is 0, we will say that this is a factor. If the remainder is not 0, then we will say it is not a factor, okay. So the first step is we want to find the 0 of x plus 1. So I'll write it at the top here. 0 of x plus 1 is x plus 1 equals 0. Therefore x equals minus 1, okay. So we equate the binomial to 0 and solve for x, and that gives us x equal to minus 1. So clearly if we put x equal to minus 1, this expression becomes 0. Minus 1 plus 1 is 0, Okay, so that's the 0 of the binomial, which is the divisor, which is going to divide the polynomial. And we basically have to evaluate the polynomial p of x at the value of x equal to -1. So we will find p of -1, so that's -1 cube plus -1 square plus -1 plus 1. So -1 cube is -1, -1 square is +1, so +1, -1 plus 1. So we have -1 plus 1 -1 plus 1, so that means it is equal to 0. So therefore x plus 1 in this case is a factor, okay, of this particular p of x. Okay, similarly we'll do it for the second polynomial. So you have p of -1 for this also, so it will be -1 power 4 plus -1 power 3 plus -1 square plus -1 plus 1. So -1 power 4. So if the power is an even number, the negative number will always be positive, so that will be 1. -1 power an odd number will be negative, so plus -1 is -1. -1 square is +1, so plus into +1 it will be +1, and -1, and then the final +1. So we have 0 0. Okay, so now we get it as 1 here, so that is not equal to 0. So therefore in this case x plus 1 is not a factor. Okay, so it will be a factor only if p of a is equal to 0. In this case it is not equal to 0, so therefore x minus a, which is x minus -1, which is x plus 1, is not a factor of this particular polynomial. Okay, let's again check for this third example. So again we are going to evaluate this at -1. Why we are evaluating at -1? Because our binomial given is x plus 1. So when we equate that to 0 and find x, we get x equal to -1. So evaluating it as -1, so we get -1 power 4 plus 3 into -1 power 3 plus 3 into -1 square plus -1 plus 1. So -1 power 4 is 1. 3 into -1 cube. -1 cube will be -1. -1 into 3 will be -3. And -1 square will be +1 into +3 is +3. And then we have -1 and then a +1. Okay, so again in this case -3 and +3 is 0, -1 and +1 is 0, but we have a 1, so that's 1, and that is not equal to 0. Therefore x plus 1 is not a factor of this, also is not a factor of this particular polynomial. Now let's look at the last one. Again here we are going to evaluate p of -1. So basically we are finding the remainder. If the remainder is 0, we will say x plus 1 is a factor. If the remainder is not 0, we will say it's not a factor. So it will be -1 power 3 minus -1 square minus 2 plus √2 into -1 plus √2. So let's evaluate that. So -1 cube is -1, minus -1 square will be +1, so that will be 1 as it is. So this part we can multiply the 2 with the -1, so -2 into -1 will give us +2, so that's +2. And then we can multiply the -√2 with the -1, so -√2 into -1 will be +√2. plus root 2 plus root 2. The last term is plus root 2. So we have just opened up this bracket here. Okay, this bracket, 2 into minus 1 is minus 2. So minus of minus 2 is plus 2. And again, root 2 into minus 1 is minus root 2. And minus of minus root 2 is plus root 2. And then we have the final root 2 term here. So that evaluates to root 2 plus root 2, which is simply 2 root 2, and that is not equal to 0. So therefore, in this case also, x plus 1 is not a factor. Okay, so we have seen now how to check whether a polynomial or a binomial is a factor of a polynomial or not. So we basically take the 0 of that binomial and then evaluate the polynomial at that 0, at that value of 0. So the 0 of this binomial is minus 1. So we substitute minus 1 into the polynomials and check whether it evaluates to 0. And if it evaluates to 0, the binomial is a factor. If it evaluates to some other number other than 0, then we'll say it is not a factor. Okay, let's move on to the next set of problem. So again here we are, it's something very similar to the previous question, and we are given the binomial g of x, and we are asked to check whether this g of x is a factor of the polynomial p of x or not. So the first thing is we will get the 0 of g of x. Let's say here 0 of g of x is evaluating g of x to 0, that is x plus 1 equals 0, and solving for x, that gives us x equals minus 1, and we will substitute that value of x in the polynomial. So now we will find p of minus 1, and p of minus 1 in this case will be 2 into minus 1 cube plus minus 1 square minus 2 into minus 1 minus 1, which is equal to 2 into minus 1 cube is minus 1. So minus 1 into 2 will be minus 2 plus minus 1 square is 1. Minus 2 into minus 1 will become plus 2, and then we have a final minus 1. So we have minus 2 plus 2, and which is 0, and plus 1 and minus 1 is 0. So effectively this is equal to 0, and since it is equal to 0, so therefore we can say that g of x equals x plus 1 is a factor of p of x. Okay, the same thing goes here. So again we will equate g of x to 0, so that is x plus 2 equals 0. So that will give us x equals minus 2. And now we will evaluate the polynomial at minus 2. So p of minus 2, that will give us the remainder. And if this remainder is 0, then g of x is a factor, otherwise it is not. So this will be minus 2 cube plus 3 into minus 2 square plus 3 into minus 2 plus 1. So minus 2 cube is minus 8. Minus 2 square is plus 4. Plus 4 into 3 is plus 12. And 3 into minus 2 is minus 6 plus 1. Okay, so we have, does this evaluate to 0? That's 12 minus 6 is 6. Minus 8 plus 6 is minus 2. Minus 2 plus 1 is minus 1, which is not equal to 0. So therefore we will say that therefore g of x equals x plus 2 is not a factor of this particular p of x. Okay, so this is the procedure to find the to check whether a given binomial is a factor of a polynomial or not. So let's do one more example of this. Again, we have g of x as x minus 3, so we need to find the 0 of g of x. So we will equate g of x to 0. So that will give us x minus 3 equals 0. And we solve for x, so that gives us x equals 3. So we need to evaluate the polynomial at that 3. So p of 3, which will be 3 cube minus 4 into 3 square plus x equals 3 and plus 6. So 3 cube is 27. That's 3 into 3 into 3. So that's 27. 3 square is 9, and 9 into 4 is 36. So it's minus 36 because there's a minus 4 there. And plus 3 plus 6. Okay, so 3 plus 6 is 9, and 9 plus 27 is 36, and 36 minus 36 is 0. So therefore we can say that g of x, because p of 3 is equal to 0, so therefore g of x equals x plus 3 is a factor of this particular p of x. Okay, so we have seen how to check whether a given binomial is a factor of a polynomial or not. Okay, now the third problem deals with finding the value of k in the polynomial, given that the binomial is a factor of the polynomial. Okay, so in each of these cases, all we have to do is we are given that x minus 1 is a factor, so therefore the 0 of x minus 1, so we'll first find the 0 of x minus 1 is equate x minus 1 to 0 and solve for x, so that gives us x equal to 1. Okay, so x equal to 1 is the 0, and we have to since x minus 1 is a factor, so we are given that it is a factor, therefore since x minus 1 is a factor, then p of 1 equals 0. So that means p of 1 is basically 1 square plus 1 plus k equals 0. So 1 square is 1 plus 1 is 2. So that means 2 plus k equals 0. Or in other words, we get k equals minus 2. So we are able to solve for k here, and we get the value of k as minus 2. Similar approach for this one. So again, we are given x minus 1 is a factor, so x equal to minus 1. So I'm not going to write this thing because it's the same factor here. So x equal to 1, that is, okay, x minus 1 equal to 0, so therefore x equal to 1. And we need to have p of 1 equal to 0 because x minus 1 is given to be a factor, so therefore the remainder must be 0. So p of 1 equals 0. So what is p of 1? So that's 2 into 1 square. So in place of x, we are putting the number 1. So 2 into 1 square plus k into 1 plus root 2 equals 0. So now solve for k and we'll get the value of k. So that will be 2 plus k plus root 2 equals 0. So that will give us k as, we take all the other terms to the other side. So we take the 2 to the other side, we get minus 2. And the plus root 2 to the other side, that becomes minus root 2. So k is basically minus 2 minus root 2. Okay, so that's the value of k for this particular case. And we have one more or two more examples here. So again, we are going to evaluate the value of k given that x minus 1 is a factor. So since x minus 1 is a factor, so we have x equal to 1 and p P of 1 equals 0. So therefore we'll have P of 1, which is k into 1 square minus root 2 into 1 plus 1 equals 0. So k into 1 square is k minus root 2 plus 1 equals 0. So that will give us k to be equal to, take all the other terms to the other side. So minus root 2, when it goes to the other side, it becomes plus root 2. And plus 1, when it goes to the other side, that becomes minus 1. So k is equal to square root of 2 minus 1. Okay, so that's the value of k that we get here. Again, the idea is we are given that x minus 1 is a factor, so therefore the remainder must be 0. So p of 1 equals 0. So we just put p of 1 equals 0 and solve for k, and we obtain the value of k. Okay, so similar thing to be done for this last problem as well. So x equals 1, since we are doing x minus 1. Okay, we are given that x minus 1 is a factor for each of the cases. So x minus 1 equals 0, so that will give us x equal to 1, and p of 1. Okay, again let me write that statement. Since x minus 1 is a factor, p of 1 equals 0, that is the remainder is 0. So p of 1, which is k into 1 square minus 3 into 1 plus k, and that equates to 0. Okay, so now we have k into 1 square is k minus 3 plus k equals 0. So k plus k is, that's 2k minus 3 equals 0. In other words, we take the 3 to the other side, so minus 3 to the other side, it becomes plus 3. So 2k equals 3, or k equals 3 divided by 2. Okay, which is 1.5. So we are able to solve for the k, given that the binomial x minus 1 is a factor, in which case the remainder is equated to 0, and solve for k. Okay, so this is the procedure. And so basically what we have seen today is only use the factor theorem to check whether a given binomial is a factor of a polynomial or not. Okay, we have not done any factorization as such in today's video. Okay, in the next video, however, we will be factorizing different polynomials and obtaining the different factors for the given polynomials, and we'll see how to go about that in the next video.